Let me just briefly. Okay, so before I start, actually, so don't take notes. So I will make some have notes available once I can figure out how to print it and so on. They haven't been proofread, so and I'm working on them now, so they won't be perfect. So if you find some mistakes, then let me know. Right? And so they will be available hopefully later today. So forget about taking notes. Just try to follow what I'm doing. So just to briefly recapitulate where we are. So what I argued last time is that well, magnets typically they arise from models or from systems of correlated electrons, and in some kind of strong interaction, strong coupling limit, you get these quantum spin models. Okay, and as I said last time, so these quantum spin models are generically quite difficult to solve because there's no small parameter, and they are not related in any obvious sense to free theories in general, because they're interacting spins, not bosons or non-interacting fermions. However, if there is order, so if there is long-range order, then you can work out the physics that accompanies this order. Yeah? So the physics of the order itself, the magnetic long-range order, and the physics of the Goldstone modes that accompany this order by simple approaches. So can work out physics related to the order, the long-range order, in a simple way. Yeah? So that's what we did last time. And then I said, well, okay, in no dimensions, so typically in one dimension for basically any quantum spin chain, but also in two dimensions, for example, if you're at finite temperature, this approach here actually doesn't apply because there is no long-range order, and then you have nothing to expand around. Yeah? And then life becomes more interesting because everything is dominated by fluctuations. And what we want to do now is we want to study so the simplest paradigm of one of these quantum spin chains, which is this spin 1/2 Heisenberg XXZ chain, which is the type of Hamiltonian I derived for you on Monday from the Hubbard model, but I generalize it a little bit by allowing for what's called an exchange anisotropy. Okay, so I don't take S dot S, but I allow the exchange to be anisotropic in one direction. Yeah? And so this basically typically arises if you have a crystal of a low symmetry. Yeah? So then if you start with the appropriate electronic model and go through this strong coupling expansion as we did on Monday, you will get some interaction which is not isotropic in spin space, but anisotropic. And this value of delta, what precisely it is, depends on the system you're interested in. So in many cases, it's very close to 1. It might be 0.99 or 1.01. It also can be a quarter or something like this. Yeah? So, or it can be 7. Yeah? So in different physical realizations, this varies quite widely. And then I also will consider a magnetic field. Just have to make sure I get the right sign. Plus H, sum J, and J. So I will be interested in this Hamiltonian. Okay? So in a sense, this value of delta, so to speak, nature gives me through the crystal I'm interested in, and H I can put just in the lab, I just apply magnetic field, and so this is a tunable parameter which is very easily changed experimentally. Okay, so now Martin will teach you, well, many things that are very interesting about this model. So in particular, I think he will derive for you or show you how to obtain the zero temperature phase diagram. So as a function of delta and magnetic field. So that phase diagram would look somehow like so. There's some special points, so here's -1, here is 1, and then here it would be 1, and here would be 2. And then, so I think the way I have to do it is like so. Yeah, so there are 3 phases. There's this phase, which is a ferromagnet. It's very easy to understand. If delta goes to -infinity, you just have to retain this term. So what you get is a ferromagnetic Ising model. Yeah? And then ground state is classical, all spins point in the z direction. So it's a saturated ferromagnet. And that's the nature of this phase. Okay? And typically here, in this region, in the interior of this region, excitations will have a gap. Alright? Which, once again, if you think about the Ising model, it's kind of clear because if you flip a spin, it costs a lot of energy. Okay, so then the other phase, which is very easy to work out, is this one here. This is an ordered antiferromagnet. What happens there is delta is very large. And once again, you can work out what the physics is by just taking the limit delta goes to infinity. So then you get a classical Ising model, but now an antiferromagnetic one, which means your spins point up, down, up, down, up, down. Okay? And that's indeed, so there's an order parameter. The order parameter is essentially SZJ, expectation value is -1 to the Jm. Classically, there are 2 ground states, up, down, up, down, up, down, up, down, and down, up, down, up, down, up, down, up. And then they're related by Z2 symmetry, yeah, which are rotations by pi around the Z direction, which is a symmetry of this Hamiltonian. And there's spontaneous symmetry breaking, which breaks the symmetry, and you also break translational symmetry by one side. Okay? So here you have this long-range antiferromagnetic order. That's the second phase. And then the third phase is the one in between. And this is called the Luttinger liquid. And what this means, I will derive for you. So this is a critical theory, as we will see. Yeah? And it's described by some conformal field theory. So correlation functions will decay like power laws, and the exponents of these power laws will be continuously varying as functions of H and delta. And one of the things Martin will show you is how to calculate these exponents from the exact solution. What I will show you is that correlation functions indeed decay as power laws, as advertised. Alright, so these are the 3 phases. Now, one thing to always keep in mind, so this was the zero temperature phase diagram. Okay? And now it's a one-dimensional system, so in one-dimensional systems you are allowed to break discrete symmetries at zero temperature, but you're not allowed to break any symmetries at finite temperature. So that tells you immediately, if you have even a small temperature, this order here has to melt. Yeah, it has to be wiped out. So this phase diagram only holds at zero temperature. At any finite temperature, this phase boundary here disappears. And all you get is essentially a crossover between 2 regimes. Now, there always is an expectation value, which is the smooth magnetization. Yeah? But this has nothing to do with spontaneous symmetry breaking or such thing, because it's explicitly in the Hamiltonian, And by applying a magnetic field, you explicitly select a direction in spin space. And then, of course, you're allowed to have order in that direction. So keep that in mind. This is quite general. Also in other models that you will encounter, Ising models and so on and so forth. So the action is at 0 temperature, yeah, where interesting things happen, like spontaneous symmetry breaking, etc., etc. Finite temperature is quite different in many ways from 0 temperature because order cannot persist. It gets wiped out. And therefore, to understand finite temperature from 0 temperature is a bit of a challenge. Okay, so that's the model we want to study. Now, I thought there was a colored chalk because they did ask for it.
Sorry?
I thought there would be colored chalk because
yes, but
he ate it already. Okay, so they didn't use it all already. So what we will do in order to make some progress here, we will focus initially on this regime here, when delta is small. Yeah? So you'll see in a moment, so that when delta is equal to 0, you can solve this model very easily. Yeah? So it becomes a rather simple exercise. So we can work out exactly what happens here. And then what we will do is, we will consider what having a non-zero delta does. So we take this into account, which will give us the physics in some slice around delta equal to 0. And once we have done that, by a continuity argument combined with the elements of the exact solution, we can actually work out what happens everywhere in this phase. We can also understand this phase transition here, and we can also understand this phase transition. Okay, so by starting here, you basically anchor your approach to something which is completely understood, yeah? And then you can extend it essentially through the entire largely liquid phase. Okay, now, so far so good. So that's the plan, what we want to do. So now, the method we will use to analyze this quantum spin chain is we first will map this theory from spins to spinless fermions. So I will show you now this spin model is actually equivalent to a model of interacting spinless fermions. It's quite a useful equivalence. Okay, and the advantage is fermions, you have canonical fermion creation annihilation operator, which are much easier to handle than quantum spins. And what we'll do then is we'll analyze the model on the level of this interacting fermion theory. So this mapping is called a Jordan-Wegener transformation. And probably many of you will know this already, but let me just go through it anyway. Okay, so these are my quantum spin operators. So I have Sj alpha, Sj beta, is I epsilon alpha beta gamma, Sj gamma, delta jk. So they fulfill the usual angular momentum algebra. Okay, so now what I do is I just define some operators. As follows: L equals 1 to j minus 1 to Sj as L S minus j. Yeah. So I just define such operators. Yeah. And Cj dagger is just the Hermitian conjugate. Okay. So essentially, what I do is here's my first site. You can choose any site you like, so I just started one. Yeah? And then you put such a string, so you put the SZ operators here, 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 you multiply them, and then all up to site j minus 1, and here you put your S minus j. Yeah? So this is a non-local operator in terms of the spins, because it involves spins on this entire segment. Alright? Now what you can check And this is what I was told by one of the organizers. I'm supposed to give you, is there a problem? No? Okay. I was told by one of the organizers I'm supposed to give you exercises. Okay, so I will start giving you lots of exercises now. And if you don't like that, complain to Pasquale. He's the help. So, first exercise, just check, verify that these operators fulfill canonical anti-commutation relations. Yeah? So just verify this. It's straightforward, so you just use this algebra essentially. Yeah? The spin commutation relations and, Sj alpha squared is a quarter. So we're dealing with spinor halves. So just using these two relations and this definition, you can show that these operators just defined in this way are spinless fermion operators. Okay, so that, if you haven't seen this before, you should find this interesting because it tells you that there is a very close relationship between spinor halves and spinless fermions in one dimension. So note, when I define this transformation, I actually make use of the one-dimensional structure of my lattice. So this trick does not work in 2D and 3D. You can try to generalize this Schrödinger transformation to higher dimensions, but it becomes much more complicated. Yeah, so you don't get a simple mapping between fermions and spins. So, now the next thing you can do is you can simply invert this transformation. That's the next exercise. Okay, so what you want to do is you want to express the spins in terms of the fermions. And I'm giving you the answer, and it's an exercise for you to check this as well. So this is C dagger J, Cj, I suppose minus a half. Yeah? And the S minus J becomes L equals 1 to J minus 1. And here I have C dagger L, CL minus a half. 2 C dagger L, CL minus 1 is a factor of 2 Cj. So that's the inverse transformation. Yeah? Once again, you can just check this by using these definitions, plugging them in there, and then basically what you see is these string operators here, they cancel. Then, next exercise, just show that you can write this product here as an exponential as e to the I pi, and here you get L equals 1 to J minus 1, C dagger L, CL minus 1, Cj, which is the usual form this transformation is given in. Yeah? And essentially what you have to use, the exponential of the operator is usually, as usual, defined simply as the power series. And because these are spinless fermions, if you take the number operator squared, it's the same as the number operator. So that's basically what we use. Okay, so we have this. Now, just use these relations to rewrite the Hamiltonian, which I call h of delta and little h, in terms of spinless fermions. Yeah? So you just plug this in now. All right? Then that's the next exercise. You do a little bit of a calculation. It's rather straightforward, and I'm just going to give you the answer. There's really only one point that needs to be discussed here. So, okay, so J equals 1 to L minus 1. Here I get minus J over 2, C dagger J, Cj plus 1 plus conjugate conjugate. Okay, so that would be the S plus S minus plus S minus S plus term. Then plus J equals 1 to L. And here I get J delta Nj minus a half Nj plus 1 minus a half. So this is just delta times J times Szj times Szj plus 1. Okay, so that's also clear. Then the magnetic field term is also clear, so that's just H Nj minus a half. Yeah, so you see this is the notation I introduced there. Okay, and now come the boundary terms. So I want to impose periodic boundary conditions. So I'm on a ring. This is side 1, side 2, side L. Okay? And what I've written here is essentially what happens along the ring, and everything is fine. The difficulty arises now because I have a term which is S dot or S times S, so Sx L times Sx1 plus Sx Syl Sy1. So essentially the exchange interaction on this link. Yeah? And on that link you have a problem because now your Jordan-Wigner string actually stretches all the way around and it doesn't cancel. Yeah? So the boundary terms plus they can be written in such a form. Well, okay, so let me first write it like so. So J over 2 Cj by L C1. Well, let's try that. E to the minus I pi L equals 1 to capital L and L minus 1 plus Hermitian conjugate. And so what you see, what you get there is a hopping term. Yeah, so you would hop from here to here, which is absolutely fine. But the string doesn't cancel. Yeah, so there's this non-local operator which is still lurking around. And then you might think this is really bad because this operator actually lives on this entire chain. Yeah? And you don't have the problem for the interaction term because the interaction term that was just Sz, which is local in terms of the fermions. Okay? Now, I will assume that my lattice has an even number of sides. Okay? This is not really a big restriction because in the end of the day you're interested in thermodynamic limits of very, very large L, and you can show, although this is actually not as easy as you might think, that L even and L odd, as far as physical observables are concerned, give you exactly the same physical observables. That should be the case because otherwise you could measure some macroscopic property, let's say, of your sample and tell whether it has an even number of sites or an odd number of sites, which is not very likely. Okay, so I will just assume I have this, and this is really kind of not a serious restriction, but it makes analysis a little bit easier. The first thing, if L is even, I can drop this minus 1. Alright, because this gives me e to the minus I pi or e to the I pi L, and then if L is even, okay. Good, so we erase this. Now, here, this is the number operator of fermions. Okay, and a very important property is that the Hamiltonian commutes with the number operator of fermions. So that basically tells you the fermion number is conserved. Okay, and that means it's legitimate to consider even fermion number or odd fermion number separately, because the Hamiltonian doesn't mix them. Alright? So you basically block diagonalize the Hamiltonian into blocks for even fermion number and a block for odd fermion number. Okay? And if you do that, then what you see is this complicated looking term becomes very, very simple. So now if n is even, yeah, so n is the eigenvalue of n hat, so it's the number of fermions, of spinous fermions in my system. Yeah, and because of this it's a good quantum number. If n is even, then what do I get here? So I get no sign. Yeah? But then you see, so now the hopping term has a plus sign. Whereas in the bulk, I have a minus sign. Yeah? So in other words, along this link, my hopping has their own sign. And that basically means my boundary conditions in this sector are anti-periodic. So here I have anti-periodic. In other words, CL plus 1 is minus C1. Just a moment. Okay. So I have periodic, anti-periodic is even, so this is right. Okay, and on the other hand, if n is odd, we have periodic boundary conditions. So here I would have CL plus 1 is C1. Okay, so in other words, when I map my spins to the fermions, I get a perfectly fine interacting fermion theory, and the only subtlety is I have to consider two allowed sets of boundary conditions. I have periodic boundary conditions for states which have an odd number of fermions, and I have antiperiodic boundary conditions and I have an even number of fermions. Okay? So you just have to keep this in mind.
Sorry, so you're just doing this to get a sensible Hamiltonian?
To get a sensible Hamiltonian, I mean, I don't have a choice. Yeah, because you see, what I'm doing here is the following. So I have applied this transformation. Yeah? So, and I've gotten the Hamiltonian I got. Yeah? And essentially what I have to specify on the level of the wave function, let's say the wave function has to be single value. Yeah? So I have to specify what symmetry properties my electronic states have if I go around once. Yeah? So on my states I have to impose some boundary conditions. They're either periodic or antiperiodic, and what the transformation tells me which ones I have to choose. Yeah? But I don't have a choice here. Yeah? So this is really dictated by the fact that I'm starting with a spin model with periodic boundary conditions. And once again, this kind of complication of subtlety is completely generic. It happens also in other spin models which are solvable by addition of the Beagle transformation. And the fact that you have different sets of boundary conditions also in conformal field theory, this is quite standard. So Professor Musano will teach you all about this, I'm sure, in his 4 lectures or whatever he has. So now where are we? Yeah. Okay, so now I can write for you what the Hamiltonian actually looks like, and I think this is where the question came from. If I define the fermion operator in this way, the Hamiltonian takes a nice form. Yeah, so I can write it like so. Okay, and so now that all traces of these boundary conditions are disappeared, which is where the question came from, but they're still there. Yeah, they don't show, but they're there, and I will have to deal with them repeatedly. Okay, now this is now a fermionic theory, a fermionic Hamiltonian, which is equivalent to our quantum spin chain. And so here, the physics of the model can be read off very easily. So this is just a hopping term, a tunneling term, Yeah, so that's a free theory. You know, cosine value, you can solve it by Fourier transform. This is just a density-density interaction. So if you have two of these spinless fermions on neighboring sites, they either repel if delta is positive, or they attract if delta is negative. All right, and this is a chemical potential for these spinless fermions. Yeah. Okay. Do you have any questions so far? Okay. Now, in order to solve this, we first look at the free theory, as we always do. I mean, so the advantage of this formulation is now you basically can open your favorite textbook on many particle physics, where you start with free fermions or free bosons, and then kind of try to develop a perturbation theory. If you try to do the same here, it wouldn't work, yeah, but you could try. So in one dimension, perturbation theory still behaves, so if you were to do that, you would find some problems. That's not what we're going to do. So the XXZ chain at delta equal to 0, so that's the first thing I want to discuss in a little bit of detail, probably more detail than you'd like, but there's a reason for this. In order to anchor what comes afterwards. Yeah? So I will spend a fair bit of time now talking about a free theory. But the kinds of things I will do are probably not things you really have thought about before. So, if delta is equal to 0, we can diagonalize h of 0 little h by Fourier transform. So what we do is we go to Fourier space, so we define C of k is sum j equals 1 to L e to the I, or let's do it properly, kn j Cj. Yeah? And then the inverse transformation would be Cj is 1 over L kn e to the minus I knj C of k. So I just go to Fourier space.
So what thing xn mean?
I was just about to ask you that. I was just about to ask you that. Very good anticipation. So what is the index n? I'm in a finite system. Yeah? So, in a finite system, momenta have to be quantized. So, the allowed values here are what? And it's a trick question, which is why I was about to ask you. Depends on the boundary. Depends on the boundary condition. Exactly. So, it's 2 pi divided by L, and then here it's either n, yeah, or 2 pi divided by L, n plus a half. And now it depends whether your boundary conditions are periodic or antiperiodic. Yeah? But then n, we can take it here to run from minus L over 2 to L over 2 or something like this. Probably L over 2 minus 1, let me just check. Well, I take it from 1 to, no, it doesn't really matter. So let's do it like so. You just have to choose a Brion zone. So I take it from minus pi to pi, I could have taken it from 0 to 2 pi, it doesn't matter. Yeah? But, so this is a reasonable choice. Okay, so what you have to keep in mind now throughout, things are easy, but things are only easy if you stay in a given sector, either even fermion number or odd fermion number. Then you can just work it through. Okay, so the Hamiltonian, in terms of the Fourier modes, simply becomes now the sum over Kn. Here I have something which I call epsilon of Kn, C dagger of Kn, C of Kn. Yeah, an epsilon of Kn, so that's my single particle dispersion. So that would be something like minus J cross K, and then probably something plus H prime, or what do I call it? Plus H, yeah. because I've set delta equal to 0. Okay? And now, so you have diagonalized the Hamiltonian. So now we can start talking about what is the ground state, what are excited states, etc., etc. So this is just a cosine band. Yeah? So if I've got the Brillouin zero minus pi to pi, 0, so it somehow looks like so. Yeah? So by tuning h is a chemical potential, you move your band up or down. Yeah? And then, so this would be epsilon of k, this would be k, and so you have zero energy states around some wave number, which I call kf, and minus kf, which depends on h. Yeah? So that's just a single particle dispersion. And then, as you all know, the ground state, if you have a free theory like this, is always obtained by filling all the negative energy single particle states. Right? So what you have to do, there are lots of negative energy single particle states, and in the ground state, they have to be filled. All right? So we can write the ground state, but before I do this, I should make one comment. The phase diagram that Martin has already run for them, or you're going to run for them? You have. Yeah. Has this phase transition line here. This one here, between a ferromagnet and this phase we're going to investigate now. So this is a line of phase transition. It's in the universality class of the so-called commensurate-incommensurate transition. Yeah, so that's a very famous phase transition. And one of the nice things about this really trivial analysis we're doing here is you can actually understand the nature of this transition in completely elementary terms. And the nature of this transition is, of course, always the same. So what happens here, okay, so we're here now at delta equal to 0. Okay, so we are along this line. And now what happens, you can just see by looking at the single particle dispersion. Okay? As I said, h tunes where your single particle dispersion sits. If h hits 1, yeah, so the single particle dispersion actually looks like this. So it just touches 0, but there are no longer negative energy states. Okay? That's the point of the phase transition. And now you can immediately say, okay, all the commensurate-incommensurate phase transition is, it's a transition that describes the emptying of a Fermi sea. Okay? You can see, if I'm below the transition, I have gapless zero energy modes. Yeah? If I'm above the transition, I will have a spectral gap. Yeah? And at the transition, it's the transition where my fermionic model is essentially at zero density. Yeah? And this observation also allows you, I'm not going to do this for you, but you can calculate all the critical exponents characterizing this transition. It's very easy because it's not really a many particle problem. You're working at zero density. Yeah? Now, why is it called commensurate-incommensurate? So that requires a little bit more work. So if you're in this phase, in the ferromagnet, now if you look at observables, which are some correlation functions, yeah, they will behave in whatever way, but if you look at two-point functions of spins, yeah, as a function of the distance between the spins, you know, it won't show some oscillatory behavior. Whereas in this phase here, as I'll show you in a moment, correlation functions typically show oscillatory behavior, and there is a particular scale associated with oscillatory behavior, which for the free theory is just kf. Yeah? And kf I tune by h, and therefore the scale is generally incommensurate with the lattice. Yeah? So it's not 2 pi or something like this. Yeah? So what you have in this phase, you have this incommensurate with the lattice oscillatory behavior in physical observables, so it's incommensurate. Whereas as you go through, this disappears and correlation functions become smooth. So let me just Okay, so that in the ferromagnet there's no oscillatory behavior you can just work out very easily, because the ground state, in terms of the fermions, is the empty vacuum. Yeah? So correlation functions are very easy, and they don't show oscillatory behavior. So now in this critical phase, let's just work it out. So we come back to so in the low field phase. So this would be H less than J, and I take it positive without loss of generality. Yeah. So then this Kf you can just work out from here by setting the dispersion equal to 0. So Kf is something like arc cos H over J. Yeah, and this is just some number. Then, as I said, the ground state is obtained by filling all negative energy states. So this would be C dagger of Kn on the fermion vacuum, and I do this for all Kn absolute value which is less than Kf. Yeah, and the vacuum is the state which is annihilated by these. Okay, now when I write this, there's a subtlety. What is the subtlety? So I've hidden a lot of stuff. That's a question I want you to answer. Yeah, anybody? Well, what I've written there, it's really ill-defined. I mean, so you should have stopped me. Yeah. So which Kn, yeah, do I put here? How many vacuas do I have? So we have either periodic or antiperiodic boundary conditions, and for each boundary condition I get a separate set of fermion creation annihilation operators. Yeah. So I really have two vacua. I have one vacuum which is annihilated by all the annihilation operators for Kn equals 2 pi n over L, and I have a different vacuum for the antiperiodic boundary conditions, if you wish. Yeah. And so you have to double all of this. Yeah. And by abuse of the notation, yeah, so you can basically, typically what you do is you say, well, I take this into account. Yeah, so let's say I consider my ground state in the sector with even number of fermions. Then you build the ground state from the fermion vacuum in the sector with even number of fermions by acting, etc., etc. Yeah. Or you could say I take the ground state in the sector with odd number of fermions. You can do the same construction, and the ground state is the lowest energy state. Okay, it could be even number of fermions, could be odd number of fermions. It depends really on what H is, so to speak, for a finite system. Okay? So this is a little bit ambiguous, but if you understand it in this way, that we always specify before we write something whether we have an even or odd number of fermions, it's okay. Okay, so this is the ground state. And then we now can work out correlation functions. So, for example, we can work out this one here, nj plus L. And I think all of you know how to work this out now, because, so these nj's, this is C dagger J, Cj, I express in terms of the Fourier transforms of the fermion operators. Okay. So what this becomes, it becomes a sum over 4-point functions in momentum space. So you have a C dagger K, Cp, C dagger Q, Cr, or something like this. Yeah. And you want the expectation value of this with respect to that state. And then, just to make sure that anybody is awake, so how do you calculate that? Using Wick's theorem, for example. So you can calculate using Wick's theorem, or if you don't like Wick's theorem for whatever reason, you can calculate it by just using the anti-commutation relations, and basically moving the annihilation operators through the Fermi vacuum. So then you can calculate this, and what you find, if I did the calculation correctly, this is kf over pi squared plus kf over pi delta L0, which are just some constants which are not very interesting. But then there's an interesting piece, minus 4 sine squared kf L divided by 2 pi L squared. Okay, and now this is as advertised. Okay, so this is the correlation function in this phase. Yeah. So it shows some characteristic power law behavior with distance. So the correlation becomes smaller when the 2 points are far away. But there are these oscillations which depend on the distance. Yeah? And there's a scale involved in this oscillation which is kf. Yeah? And these oscillations, they are incommensurate with the underlying lattice, so that's, okay, in the end of the day, explains the terminology. Alright? Okay. Now, we're not really interested in spinless fermions, we're really interested in correlation functions of spins. Now, do you know how to work out this?
Write these in terms of the fermions and then...
Yeah, okay, so this is essentially the same as this. Right. Okay, now what about this? Well, I'm sure some of you know the answer to these things, so just, you know, say it. Is this an elementary calculation? But if I ask like this, not. So why not?
You can write it as a debit determinant.
Yeah, okay, but so I'm getting there. Why is it not elementary? Let's answer that first.
Because of the string operation.
Exactly. So if I rewrite this in terms of the fermions, yeah, okay, so here I have psi j, here I have psi j plus L. There's a string stretching involving all of these SZs all the way from here to here. So this correlation function, if I rewrite it in terms of spinless fermions, involves fermions on all of these sides. Yeah? And now L, the distance between my two spins, I want to be large. Okay? And then what you have to calculate is now a very, very complicated correlation function in this free theory. Yeah? It's an L point function, or a 2L point function, where L becomes very, very large. So it's no longer elementary, this was just a 4-point function. But now let's come to the Chapman's determinant. Of course, what you can always do, because it's a free theory, you can use Wick's theorem to express this as a very complicated sum of terms, as you do when you do Wick's theorem. All the contractions, blah, blah, blah. And then what you can show, and this is not really the subject of my lectures, but you can rewrite this sum in terms of a determinant of a very, very nice matrix. The determinant of what's called a Toeplitz matrix, so matrices with very specific properties. And then using known properties of these Toeplitz matrices, you can work out how this behaves when L becomes very, very large. Okay, so you can still solve this, but it's a hell of a lot harder than this calculation here. And if you're interested in that, okay, so I give some reference there to a paper by White and Tracy from the 70s where this is done. Okay, so the message here is not everything is elementary, even for delta equal to 0. Okay, so certain questions you can answer very easily, like SZ is Z, you can calculate very easily, but others are complicated. Yeah, you can't do easily. I think we have our break now, so we make a 10-minute break and then we carry on. So essentially, so you have to find the functional value, but this is not really what it is. So you can